All right, in this set of videos we need to talk about actually what happens during solution formation, like what is actually occurring. And we need to kind of talk about how that involves the intermolecular forces. So let's talk about sodium chloride dissolving in water, basically typical salt water. So what's happening is sodium chloride is the solute and water is the solvent. And you throw the salt water, or you throw the sodium chloride in and the water pulls it apart and you end up with a solution. Yay! But some things do form solutions and some don't. So what's happening is we're going to talk about the energy component of this, the delta H's of this. There's not going to be a lot of math, but we're going to kind of look at the concept here. Okay, so the first thing is that the solute molecules will have to overcome their intermolecular forces. Okay, so sodium is positive, chlorine is negative. There is a very strong interaction between those. Okay, I don't know why I threw them so far apart, but whatever. Okay, so for the solute, you have to overcome some sort of force. You're going to have to put energy into this. Okay, similar idea with the solvent. The solvent, which in this case is water, is polar. I use a lot of colors here, sorry. Probably should do that right. Partial negative, partial positive. These things are going to line up so that there is an interaction between positive and negative. That's kind of how the world works. Positive finds negative, they're attracted to each other. That's pretty much it. Okay, but there is an interaction here. Okay, and so this is the solvent, which will also have to be pulled apart to make room for this solute. Both of these are positive delta H things. They're very endothermic. They require energy. Basically, you're overcoming the intermolecular forces or you're literally breaking bonds. So delta H is positive. Okay. So this shouldn't surprise you. If these things are if the water molecules are being held together, you're going to have to put in some energy to pull them apart. Sodium and chlorine is a molecule. You literally have to put energy in to break those bonds. Okay, but either way, you're going to have to put some energy into it. Well, it turns out that when you throw these two things together after they've been broken apart, the way it works is that the sodium is positive, and it will happily allow itself to be lined up with waters around it. I'm only going to draw a few. It may take more than three. I am drawing three because it seems like the right answer. Okay, it seems like a right answer. So the partial negatives all attract to the positive. And this is a better positive than these things were. So what we end up with is multiple interactions here. And the same thing happens to the chlorine. Okay, chlorine's negative, so the hydrogens are going to line up around them. I'm going to draw three again just to be consistent. Again, I am not sure that three is the right answer. I don't know how many water molecules it takes to make this thing happy. But the hydrogens are slightly positive. Okay, so there's going to be an interaction here. And for this part, I guess I'll do it this way. For this part, the delta H should be negative because you're forming new interactions, which stabilizes everything. So this releases energy. Okay, so delta H should be negative, exothermic. I guess I said it, didn't write it down. Endothermic up here. So delta H is negative, which means exothermic. So we had solubility rules in Chem 1 where we learned about whether things will dissolve just by looking at their formula and blah, blah, blah. And that's still true. There's nothing wrong with that. But this is just kind of talking about the energy component of what makes those decisions possible. Okay, so it turns out that for a given mixture, if you add up the energy required to rip this apart, the energy required to rip this apart, and the energy payoff of putting them together, if delta H is negative, a solution will form. If delta H is positive, a solution won't form. It's literally as simple as that. Of course, measuring these delta H values is really difficult, but the concept is not. Okay. So this is also why things dissolve better at higher temperatures, because the hurdle to making a solution is overcoming these forces. If you heat it all up, there's more than enough energy to go around, and everything tends to work out. Okay, so just because something won't form doesn't mean you couldn't pump in energy to make up the difference. Okay, I don't know what page we're on. Give me just a second. Page 6, this is page 7. Trying to keep it straight here, sorry. So, the next thing we need to talk about is how this relates to solubility. Okay, we have talked about solubility in Chem 1. If you need to review the solubility rules, that's fine. I'm not sure they're super immediately relevant to this topic, but that's okay. What we want to know is we want to put some numbers on here. How much solute is going to dissolve? Okay, so when we looked at solubility last semester, we just looked at yes or no. Will it dissolve at room temperature, at neutral pH, just pouring this stuff into water, will it dissolve, yes or no? Okay, so solubility is more a measure of how much solute will dissolve in a given temperature, or in a given, or sorry, not temperature, a given amount of solvent. So, as you might expect, if you have a very small amount of solute, the odds of it dissolving is very, very high. If you have a large amount of solvent, the odds of it dissolving is very, very high. So the units on this end up being grams per milliliter, which I know is density units, but what we're talking about is how many grams of solute can be dissolved in a volume of solvent. Okay, and the weird thing about this is that it is temperature dependent. We just talked about why, but we need to kind of address how that matters. Okay, so the idea is at higher temperatures, there's more energy to overcome the intermolecular forces, and you can dissolve more solute in there. Okay, so we need to introduce a couple definitions before we go too far here. We need to talk about something called a saturated solution. And this means that you are above the solubility limit, the limit of how much can dissolve. Above the solubility limit. Okay, so what that means for us, for a given temperature. Temperature matters a whole lot on this. Well, for some solutions it matters a lot. For some solutions it doesn't matter very much at all. Okay. So it is entirely possible to have something that totally dissolves in water, like sodium chloride. You guys are all probably aware that if you take a volume of water, like suppose you have a glass of water and you just keep pouring salt into it, it will dissolve, but at some point there will be so much in there that it can't dissolve anymore. You'll just run out of water molecules to hold it in place. I don't know that 3 is the right answer, but you need a certain amount of water to keep each of these ions happy. At some point, you just literally run out of water. Okay. Anything below that is called an unsaturated solution. So an unsaturated solution means below the solubility limit. Solubility limit. Okay. In terms of visualizing this, a lot of times people visualize like, oh, okay, we have sodium and it's got some waters and it's going to stay like that forever. Those are the waters that it's stuck with until the end of the universe. Yay! It is not even remotely like that at all. It turns out that it is a very dynamic situation. Okay, so solubility is dynamic. So what I mean by that is it constantly changes. So if we looked at a saturated solution, know, if you take a bunch of salt and throw it in a beaker, get some water in there, if you throw a little bit in there, it'll dissolve and it'll be a completely clear solution, and that'll be an unsaturated solution. If you keep pouring salt in there, you'll end up with a pile of salt that can't dissolve because you don't have enough water molecules, okay? And if you swirl it around, you end up with this weird little, like, kind of pyramid-y shape, okay? And what we see is that one of the easiest ways to check that this is dynamic is that what's happening is if you make this little pyramid, the crystals that are here, there aren't enough water molecules to dissolve them, but that doesn't mean that they don't dissolve. What happens is they are continually trying to dissolve, but because there's not enough water, some other salt crystals are going to have to give up their waters to make this happen. And then this recrystallizes. Okay, and it continually happens. And so if you wait, if you take some time, you'll find that if you take the same solution and just leave it as is, keep it covered up so water doesn't evaporate and all that, it'll end up flat. Oops, I can't write. Flat. Sorry. It'll end up flat because what's happening is it is completely random which ones dissolve and which ones recrystallize. But the total amount of solid should be the same. But if you swirled it around and made it into a pyramid, it will not stay a pyramid because it's random. And a random distribution ends up being flat across the beaker. Okay, it's a really easy way to like test that this is the case. The fact that things continually go dissolve and recrystallize or move forward and backwards is going to be really important in a couple chapters from now. But for right now, this is the basic concept of solubility. Okay, I'm going to stop here, and the next video is going to continue this topic, but good enough for right now.